Formation constants. This ultimately brings us back to the idea of coordinated covalent complexes. Some of them could be neutral, some of them could be positively charged, some of them could be negatively charged. And you have your octahedral, your tetrahedral, and your square planar complexes, right? So just to kind of remind you, you have your ligands, that are called fluoro, chloro, bromo, iodo, nitrito, nitro, sulfato, sulfito, etc., right? You also have your neutral ligands like aqua, amine, ethylene diamine, carbonyl, nitrosyl, pyridine, and bipyridine. But the thing is that in addition to just naming those coordinated covalent complexes and calculating the value of delta octahedral or delta tetrahedral, there's actually equilibrium values associated with the formation of such complexes. And the idea is that by definition, the equilibrium constants of formation, or KF values, are simply the values that you obtain when you take the naked metal, the ligands by themselves as reactants, and then combine them to make the complex. So the values that you see here are the equilibrium constants that tell you how likely it is for the complex to form. And of course, the larger the exponent becomes, the more likely it is for this complex to end up forming in the first place. And for some of them, the values are vastly favored to form the complex from the naked ion, right? So some of this can be attributed to the crystal field stabilization. So for cobalt 3+, which is the complex that has the the really high value right here, 33 for the exponent, the reason it's that high is because cobalt 3+ has 60 electrons. And being a low spin complex, you have all three of the bottom orbitals filled up with electrons, all 6 of them. And so you end up with a maximum number of stabilization for that particular complex. For the platinum complex, you have a D8 system that has only 4 ligands, so you end up with a square planar complex, which also gives you a really high stabilization energy overall. You can see the values are right here, negative 2.4, negative 2.46, roughly speaking. But those are not the only types of complexes you can make, right? So the first one was the amine complexes. Now you have the ethylene diamine, and these values are also pretty high. Notice that for cobalt 3, once again, the one that has the D6 configuration, you have a really high formation constant. For other ones, like iron 2+ and cadmium 2+, the ones that have lower oxidation state, the values can be lower in general, right? But nonetheless, you do have a stabilization energy that is similar to the one of cobalt 3+. It's just the fact that 2+ for iron has less of a tendency to attract electrons than the 3+ state. So the charges do get in the way, right? So the higher the charge, the higher the value of delta octahedral, the more likely you're going to want to form that complex. And the fact that you may be using second or third row transition metals also increases that delta octahedral, so it gives you further stabilization as a result of the presence of the second or third row transition metal. Now the tables of KFs, kind of keep going, and I'm going to give you a good number of them that we're going to utilize in this class. You also have the hexafluoro complexes, for which there are values given. And one thing that I want you to be aware of is that group 11, specifically silver and copper to some degree, tend to form yet one more shape that we haven't talked about until now, which is the linear shape. So you have to be aware of these particular linear complexes in order to figure out how many ligands you're going to be dealing with when it comes down to writing the equations down. The group 12 elements, groups 3A and 4A as well, so like lead, or you have your aluminum, at most they tend to have 4 ligands, 4 anionic ligands present, so you form the tetrahedral complexes with these particular metal groups. And then most others will have 6 fluorides accommodating in its metal sphere. A similar feature takes place with the cyano-ligands. You could have octahedral complexes, you could have tetrahedral complexes with group 11 elements for the most part, and group 12, and the linear for a handful of the group 11 elements. Also, since cyano is a strong field ligand, if you have a transition metal with a D8 configuration and only 4 ligands present, you can deal with the, or end up with the square planar arrangement. And the values in general are higher for the cyano ligand because it's negatively charged and it's also really strongly bound to transition metals in general, which is the reason why it acts as a very bad poison for humans, because it tends to go after key enzymes in the process of respiration that do have transition metals present in them, and so they bind to the transition metal and render it inactive to fulfill its function, and as a result of that, cells stop producing energy and we basically go dead, right? So that's what cyanide does, among other things. Now the oxalato ligand, it's also negatively charged, it's bidentate, so it tends to bind really strongly to metals that have higher oxidation state. We saw that with the neutral ligands, and it's also true here because, you know, higher positive charge, you have better traction with the negative charge of the ligand, the oxalato ligand. And then the last one, which we're going to look to some degree, is the ethylene diamine tetraacetate ligand, which actually binds by forming a hexadentate complex. You can see that it binds through all 4 oxygens and the 2 nitrogens, giving you your perfectly octahedral arrangement for your transition metal. And all the values are depicted right here, and most of them are pretty large in general, especially if the charges of the metals are high. You know, we're talking about 3 plus or so. You have a really high binding force between the EDTA ligand and the transition metal. Alright, so we're going to actually do some calculations. So I'm providing you with those tables so you can, you know, have a reference frame. But it's very likely that I'm going to provide you with those values when it comes down to the problems in the homework and the exams. But let's do some calculations, some ice-table calculations to figure out equilibrium concentrations. The idea with the formation constants is twofold. First of all, if you're trying to determine the solubility or the concentration, the equilibrium concentration of a species that is a complex ion like tetracyanozinc ion, or excuse me, tetracyanozincate ion, for this particular complex, the fact that you have a complex means that this is a Kf constant. And the idea right here is that you have to basically write the definition of that specifically Kf constant, which is you're forming the complex, but the complex gets formed from the individual naked cation and the individual ligands by themselves. So bringing those empty ligands, or not really empty ligands, but bringing those ligands that haven't been bound to anything and binding them to the naked ion is what we define as the formation constant. So this whole thing is what has a value of K of 10 to the 18. Now, because the value of the equilibrium constant is so large, we are going to assume that this goes to completion. That's going to be the assumption we're going to make, and we're going to work our way backwards from that point forward. So this is the way it goes. You have your ice table, zinc 2 plus, cyanide, and then you have your tetracyanozincate complex at the end. Initially, you start with 0.125 molar concentration of cyanide and zinc 2 plus, so those are the initial concentrations. The initial concentration for zinc is 0. Alright, so now we have to determine the change, and here's where you have to be careful. This is as a result of the fact that the equilibrium constant is so much larger than 1. This is not a minus or plus x changing concentration. This is a changing concentration that it goes to completion and is based on the limiting reactant. So you have to basically determine which one of these two components is going to be the limiting reactant. So to give you an idea, if we start with a 0.125 molar cyanide concentration, we actually require 4 cyanides for every 1 zinc. So we could actually use a conversion factor, you know, so for every 4 moles of cyanide, we use up 1 mole of zinc plus. And so the moles of cyanide are going to cancel out, and the mole of zinc will combine with the liters that you had in the molarity to generate the molarity of zinc 2 plus. And so what this is telling you is that in order for you to use up all 0.125 molar concentration of cyanide, you only need 0.031 molar zinc concentration. And that means that cyanide is in fact the limiting reactant because you have a lot more zinc present than what you have right here. So in terms of the change, you will not subtract 0.125 from zinc. You will subtract the limiting amount based on the stoichiometry. So 0.031 for cyanide, since that's the limiting reactant, that one is the one that you subtract 0.125. So this is a little bit different than what we've seen for the mice tables of acid-base titrations. And the reason why is because you now have coefficients that are not going to be 1-to-1. Alright, now with that being said, the same idea goes for the tetracyano zinc complex. For every 4 cyanides that react, you're only forming 1 mole of the tetracyano zincate complex ion. So you will not be forming plus 0.125, you'll be forming plus 0.031. Alright, so that means that your final amounts will be 0.094 molar, 0 molar for cyanide, and 0.031. Okay, now, when it comes down to equilibrium, you can't have 0 for any of the components. If you do have 0 as the concentration, you haven't quite reached equilibrium. But we have applied this rule of completion so that we take everything to the right side of the equation as depicted by the equilibrium constant, and now we're going to play a trick. Well, simply stated, what I'm going to do is I'm going to take this equation and I'm going to reverse it. So the complex ion will now become the reactant, and the naked metal and the regular ligands are going to become the products. And the moment you do that, you simply take the inverse of the Kf. So this is the inverse of the Kf. It used to be 10 to the positive 18, or 1 times 10 to the negative 18. If you divide that from, okay, so if you divide 1 times 10 to the positive 18 from 1, you will get 1 times 10 to the negative 18. And what basically we're doing now is we're taking the values that we just got from the previous example, we're taking it to completion, right? But now this becomes our new initial states. So the concentration of zinc, the tetracyano zincate ion is 0.031. Zinc 2 plus is 0.094, cyanide 0. So here's where we apply the regular minus and plus x. And the reason we're using now x's is because the equilibrium constant is less than 1. So we have minus x for the complex ion, plus x for zinc 2 plus, and plus 4x for cyanide because of the balancing coefficient. So these are your new equilibrium amounts. So, oh, and by the way, because the equilibrium constant is so much lower than 1, the minus x and plus x are going to be negligible. So ultimately, the equilibrium constant depicted here is based on 0.094 to the first power, 4x to the fourth power, all divided by 0.031 to the first power. Alright, so yes, the plus and minus x's are negligible. So we're going to end up dividing 0.094 by 0.031, which is 3.03. 4x to the fourth power is 256x to the fourth power. So if you multiply 256 by 3.03, you get 775.7, and divide both sides by that number, and ultimately raise the answer by the power of 1 over 4, you will get 5.99 times 10 to the negative 6 as the value of x. Alright, so that means that the cyano concentration will be 4 times this value, so ultimately the cyanide concentration will be 2.4 times 10 to the negative 5. And by applying this particular trick, you have actually found out the equilibrium concentrations of everything, right? And the idea is that you have to have values that are other than 0. If you have a 0, you haven't yet reached equilibrium. Alright, so with all that being said, this is the end of this lecture. We'll revisit the ice calculations one more time in the next lecture, so hopefully you'll get thorough exposure to them. So see you in the next lecture series.